So welcome everyone. Thank you for joining us on today's webinar and thanks for taking time off your day on this session on OSM Standard and product design with the OSM. My name is Taufik and I'm responsible for marketing at iWave Systems. We are also glad to have with us on this session Mr. Ansgar Hen, who has been the chairman of SGET since June of 2021, and also have along with me Mr. Emmanuel, who's the Vice President Engineering at iWave Systems. So the three of us will take you through this session for the next 1 hour. So just a little housekeeping before we get started. If you have any questions during the presentation, you can type them into the chat box on your right, and we shall get back to them right after the presentation. This webinar will be recorded and we will share you a copy of the presentation and the video in the next few days. All participants are on listen-only mode to ensure better flow and continuity for the speakers. And the total duration of the webinar will be for 1 hour with the latter 15 minutes scheduled for Q&A. So looking at the agenda of the webinar, we have a few points covering the webinar. So first, Mr. Ansgar will give us a quick introduction of SGET, the various standards, and what the benefits of SGET, and a quick introduction of different system on module standards. Then we talk about the why solderable system on module and the OSM standard, with a deep dive on OSM specifications, with a few tips and tricks for carrier card design, thermal considerations, and product design with the OSM module, and ending with the Q&A. So with this, without any further ado, I hand it over to Mr. Ansgar Hen, who is the chairman of SGET. So Mr. Ansgar, over to you.
And welcome everybody to this webinar on OSM. Please let me start by introducing you to the standardization group for embedded technologies. As said, I'm the chairman, and yeah, that's me. I'm chairman of the board since June of last year, and I'm really glad to work for this great organization that's been developing the OSM standard. I'm a really geek when it comes to technology, but moreover, I'm really into marketing. That's my main profession, actually, besides being a chairman. I'm living in Cologne, Germany. That's where I am now. And what makes me stand out is I truly believe in the power of open standards. And I bet a lot of you do too, because I think that drives our technology forward and that helps our community thrive and build better technology around that stack. So yeah, let me introduce you to the ASCAT a bit, about who we are and what we do. Our association is located in Germany, but we're international and not-for-profit organization. And of course, you may join us if you like to, because we're open to companies and to organizations from all over the world. And we're happy to have you in order to further develop our open standards, or maybe introduce new standards. If you have great ideas, just approach me or my colleagues, and we will be happy to talk to you about that one. Our goal is to collaboratively develop independent standards for embedded computer technology, which includes specifications, design guides, etc. So we're driving this change, and we have been driving this change for 10 years now. It's a decade. So yeah, there we are now. And lots of our member companies and organizations are really popular within this industry. And we're really happy to have international companies from all over the world joining us and sharing their knowledge, ranging from small companies to large chip manufacturers. They've all joined the ASCAT in order to drive open standards and drive this development. Our purpose is to define and market these standards. So yeah, that leaves me with the next slide. Our benefits. So if you would like to join us, you can have a major influence on new specifications, help us further develop those standards that exist, and maybe establish new standards. We're right now in the middle of trying to figure out something new, and yeah, please stay tuned for more details within the next half year. Bear with us. So if you join the ASCAD, what will you get? You will benefit from our logo and trademark usage. So our standards, as said, are open. You can download them from our website. You can use the specifications, but in order to market those, you will need to join the ASCAD in order to not have a copyright or trademark infringement. But what's more important to you is maybe that you can access our first level support, get first-hand information from our community for all of our standards. So it's a quite vital community, and you will have a lot of networking going on, get a lot of experience from all the people who have joined the ASCAD. And we're organized in different standardization development teams, and those standardization development teams are based around our standards, starting off with the SCT-01 about SMART. We have the Q7. We have developed the Q7 standard as a second standard. We have the embedded NUC standard. We have the universal IoT connector, and last but not least, it's the open standard module, which today's session is all about. So I would like to walk you through our standards in order to introduce you to the concept behind the ASCAD organization. Our first standard that we have developed like 10 years ago was the SMART module standard. It's a small size computer on module. And what makes this standard stand out is it's one standard for ARM and x86. It's a quite small form factor with 82 by 50 or 82 by 80 millimeters in size, and you can use ARM, x86, or even RISC processors with it. It comes with a 314 pin connector that offers lots of different features. You can walk through the spec if you like to download it from our website and see what makes this one stand out. It's been designed for mobility, but not limited to that one. But most applications are mobile applications due to the low power consumption of the SMART module, and the current standard version is 2.1.1. So it's quite actual. That's the latest update. Next one in line is the Q7 module. It's also a very small size computer on module. Almost 10 years ago, it has been established. It's a square form factor, as you can see, but we also have the micro Q7, which is a little bit different in size and relates to smaller specifications, even more low power connections. It's an industry-ready standard, which means it's a really long-established standard. We have also here the current version 2.1. It's a little bit comparable to the SMART module, but it's more cost-efficient, and it's a really interesting concept since there's also a defined cooling interface. So if you're interested in this one, feel free to get in touch with us. The third one is a little bit more special. It's the embedded NUC standard, small size SBC carrier board standard for box PCs. It's based on the Intel NUC concept. So Intel NUC stands for Next Unit of Computing. It's we've adapted this form factor to make it an embedded form factor for industrial usage, and it's typically used for Q7 or SMART carrier boards, but as you can see in that picture on the lower right, it comes with mechanical concept for housing and cooling. So this concept not only includes the dimensions and the connectors on the board, and the positions of the output, but also a mechanical concept and a cooling concept. The current version is 1.0, and as far as I know, the embedded NUC standard team is looking for new members who will help drive the change, drive the development. So any ideas are welcome there. I know that they're working on the next version of the standard there. And that leads me to the Open Standard module, which is quite a new approach to the industry. Well, there have been solder-on modules, but there has so far been no standard. And what makes this module approach stand out is it's directly solderable. It's a scalable computer module concept, which means it's not only one solderable module approach, but it comes in different sizes, and it comes with a software support system and lots of varieties. But before I continue here, please let me hand over to iWave and to the guys introducing you to this wonderful concept of open standards. And if you have any questions about the ASCAP, please get in touch with me. Thank you.
Thanks, Ansgar. That was a very exciting intro about SJET and the value addition of SJET. So just giving a quick background of iWave, of who iWave is. So we were primarily established in the year 1999 with the mission to be an embedded technology partner to companies across the globe. And over the last 22 years have built strong embedded expertise on various platforms and are completely premier partner with all silicon vendors such as NXP, Xilinx, and Intel, and have helped companies across the globe through our design and manufacturing ecosystem. So looking over the past years, you might have seen our website or the strategic focus on iWave is completely on the system on modules. So in the year 1999, we started as a pure play engineering services company. Then in 2001 is when we became a partner of NXP and Xilinx. And over the last 20 years have built a very strong partnership and are one of the top 5 preferred partners across the globe. And 2009 is when we started building system on modules on various standards. For example, the i.MX 51 base Q7, slowly transitioning to the i.MX 6 base Q7, and then having the Zinc 7020. And over the years, innovating as the silicon keeps upgrading as well. So as of 2022, we have recently launched the i.MX 8M Plus OSM with the roadmap of the i.MX 8X Lite and i.MX 93 down the year. Also focusing on the Xilinx UltraScale Plus MPSoC and FPGA system on modules. So we have a very strong portfolio of system on modules at iWave, continuously innovating on the latest standards and building the processing platforms for applications ranging from tablets to ultrasound machines to wearables. And looking at the standards which Ansgar just mentioned, so iWave has bet big on the different standards defined. For example, the SMARC, the Q7, the Micro Q7, or the OSM. So we continuously try to keep on upgrading the technologies on the similar system on module form factors, which gives customers the provision for scalability in their products. So how does a system on module help in product design? So before we get into the OSM specification, so the main reason why system on module has especially emerged over the last 2-3 years with engineers sitting across different parts of the globe, embedded system engineering and design has been quite of a hassle. So with system on modules, you're able to reduce your product development complexity. In turn, you're able to reduce your risk and time, which greatly reduces your development cost. And the second factor as of today is the supply chain. So instead of you worrying about the hundreds of components, you can integrate one system on module on your board, and the SOM manufacturer takes care of the complete sourcing complexity for the different modules on the system on module. So you have a single point of contact for your processing platform. And the system on module manufacturer also takes the responsibility of finding alternate components on a regular basis, which ensures a continuous supply of system on modules for you, which you do not have to worry about for the different processors in the backend. And the third is in terms of flexibility and scalability. So continuously upgrading with the latest SOC technology or in terms of connectivity options, SOM definitely helps reduce your development time. And last but not the least is in terms of product longevity and complete product maintenance in terms of hardware support or software support. There is continuous roadmap from the system on module vendors as well. So what are the key considerations? So this maybe lays out a key guidelines for the OSM specification. So the top 5 criteria for choosing a system or module, be it a SMARC or Q7 or an OSM. So the first one would be in terms of the form factor and environmental considerations. For example, the OSM is more fit for rugged environments with high vibrations, which we'll touch upon in the deep dive maybe a few minutes later. The second would be in terms of the electrical interfaces required, the displays, the cameras, in terms of connectivity, Ethernet or CAN. So choosing the right module. The third would be in terms of the processing power and budget. You require an AI engine running on the edge, or it's more of a processing platform. And last is in terms of the product longevity offered by suppliers and the interoperability amongst suppliers. So as of today, it is scary for any organization to rely on one single vendor for any of their components. So having a constant source of options for system on modules and being completely flexible amongst those options is a key factor in product development today. And why opt for industry standards? So what SZ is doing, what is the main value addition from SZ is the key concept of the underlying technology, where if you say 1 + 1 is definitely greater than 2. So you have interoperability amongst multiple suppliers. So you have the option to choose a SMARC or a Q7 module between multiple suppliers, and you have the dependency and reduced risk. And the second one is in terms of you have a modular platform, so you're able to easily upgrade technology over technology, provided the complete career card design is taken care of. For an example, you want to upgrade your gateway from an i.MX 6 to an i.MX 8. You're able to easily do that as long as your product is built on an industry standard specified module. So now coming to an option of why a solderable SOM is required. So these are the key 4 points. So the first one is in terms of environments where there's lot of shock, vibration, and there is a reduced risk in the connector. And you have the second is in terms of form factor, where you have the compact design with reduced height constraints, and provides the option for technology scalability, which is in terms of multiple modules on the same carrier card. So potential applications of an OSM module. So the main advantage of the OSM module includes the PCB solderable module, which offers resistance to vibration and offers a very high pin to area ratio, which we'll cover in the next slide. So looking at the applications, for example, in-flight tablets, where I'm sure all of you would have witnessed severe vibration at time of takeoff and landing. So you need products which are capable of withstanding the vibration and do not give away. The second is in terms of heavy machinery, so CNC machines, drones, again landing and takeoff and in the air, connectivity clusters for two-wheelers or four-wheelers or the upcoming electric vehicles, where there's a lot of definitely huge vibration on the roads, and heavy equipment machinery displays. So where you have in the rugged environments such as the mining areas, you have a lot of vibration. So these are a few potential applications of the OSM. So now I'll hand it over to Mr. Emmanuel, who's Vice President of Engineering at iWave Systems, to take you through the specifications and a few product design characteristics.
Thank you, Taufik. My name is Emmanuel. I take care of the complete system on module development at iWave. So we breathe in and out on the modules. More than 10 years before even this SZ standard was, this committee was formed. But then once this standard was on board, and we were very happy to be a part of this ecosystem. And thank you everyone for joining this morning from European friends, and good afternoon and good evening for our Asian friends and friends from India. So next 10-15 minutes, I'm going to little bit get into deep dive on OSM and some of our experiences on our first module design. So we are one among the earliest to bring out the OSM module. So I'm going to share some experiences. So this specification, as you are aware, it was launched in 2020, late 2020, at the midst of this pandemic, and it was very brand new now and very future proof and versatile standard for the very small size and low cost embedded computer modules. If you look at the specification, this was completely machine processable actually, and it does not, you don't have to need a connector. That is the main difference from this specification, and it completely predefined by the committee, the hardware interfaces, and it's a fully open source. That helps a lot in terms of open source, so anybody can design, do, and the ecosystem can evolve. And there are two different heights are defined in this standard. So one is the standard height you see on the left side, and right side you see the extended height. So in the standard height, so the module is directly soldered onto the baseboard or the carrier board, you call it. And then the extended height, yeah, there is a small spacer PCB you can have. It's kind of a dummy PCB just to pass through the electrical connections. But this serves the purpose, so you can have a component at specific areas in the bottom of the BGA module. So the complex SOCs, you need definitely a small discretes, especially the decaps kind of stuffs. So the just allow a small spacer PCB so that you can have some areas you can have small components. So when you have a standard height, you can have much smaller. With the extended height, there's another PCB adder kind of height is getting added. Yeah, and if you move on to, there is another option the specification provides. You can also have a PCB cutout area in the carrier board. So if you just see in the previous slide, you can still have only the standard height. You don't have to have a spacer PCB, but you can cut out in the carrier board itself. But the carrier board cutout areas were specifically defined in the specification itself, and one needs to follow that. So this means the spacer PCB is definitely not required when you go for this method. And in terms of sizes, and it was the committee has spent a lot of effort in terms of scaling up, and it is very future proof. That's why we call it very future proof. It defines 4 different sizes. You call it a 0, and S for small, and M for medium, and L for large. And the 0 is very small size. Even nowadays you see the SOCs you cannot get in 3515, correct? Maybe the microcontrollers you can get, but in the microprocessor side, and the chip sizes were quite bigger. And then the smaller size, 30 cross 30, with 332 contacts. If you look at the SMARC, which is the smaller SMARC, yes, which is 82 into 50, which is more than double, which is just give 314 pins. But this is a very nice, within a very small area, you get a lot of contacts. And in the medium, you can have a 30 cross 45 with a 476, and large 45 at 662 balls or pins you can get in the bottom. And this is structured such a way that so one can develop a carrier board can accommodate from the 0. You see the red color mark, which is the center, which is just a 30 cross 15, and then the blue one which incorporates 0 and then small, so which incorporates both. And the medium, which is orange color you see, which is a 30 into 45, which incorporates both the 0 size red and the small, and then medium, similarly large as well. So this is a very nice concept. It is very future versatile, so one can go all the way to 662 pins within just 45 mm into 45 mm, which is much smaller than the other standards available like Q7 or SMARC, and even for the beyond the jet standards where you get COM Express Mini, and it's much smaller in terms of size. So in terms of the balls in the behind, so the specification offers 3 different types, like a FTGA, the fused tin grid array, and ENIC LGA, and also the PGA package. So mostly our choice was actually ENIC LGA after talking to multiple PCB vendors. You can also opt for a PGA, but when we check with the PGA balls cost, so when we go with a large size, with the 662 balls when you add, so it's quite a bit of adding the cost to the module. So based on our exploration, when we did this module with multiple PCB vendors, and we settled at ENIC LGA at a very sweet spot at the cost. So I'm going to run through a few of the design considerations, correct? It's whether it's a carrier board or on the SOM, whether anybody develops. And there are some areas you can look at it. So one of the thing is like provision of the space in the carrier board for accommodating the SOM bottom assembly. So we have done some experiment with the decaps on the top and also in the bottom. Obviously, we settled at decaps in the bottom, especially on directly on top of the power pins, which gives very good switching efficiency. So we would prefer the bottom also decaps mounted in the areas where cutout is given. But when it comes to versus spacer PCB or carrier cutout option, which one to choose? Right. So in terms of spacer PCB, so that is also we did two different spacer PCB, one for the large size, another for the small size. Correct. But the cost of the spacer piece is very feeble. It's like about 10 or 15 cents though, but it adds up a lot of assembly cost. So when you put a spacer PCB, you have to tend to do double your the soldering joints are getting doubled in terms of large SOM. If you take, so you have a 662 pins which become doubled because of the spacer PCB. Obviously the assembly cost is more, though the PCB cost is less. But if you go to the carrier cutout options, so you save the cost of the spacer PCB and also the assembly cost, but at the same time you have a lot of holes. So some like it, some did not like it, because if it is a small module, it's fine. But if you go for the large modules, you can have at least 3 cutouts in the carrier board, so which looks a little bit odd. And then when you provide the cutout in the carrier board, we would propose you provide for all the OSM form factors, correct? So if your carrier board is for not like a very size constrained applications, even though you may develop the 0 size or the smaller size or medium size, we would suggest to include the pinout for all the way to the large. Not only that, you can have a cutout for all the 3 areas, right? So that you have the complete scalability and flexibility. And the specification also define a smaller area for the RF area where you can bring out your RF antennas, right? Yeah, the module size is very small. You have very much less options. So once you put a processor, memory, power management, correct, you have left with very, very less space. But we were able to even add the Wi-Fi and Bluetooth module into the large size of the first module. So it was a nice, because it's already predefined for the RF area. And another area we have checked is there is no specific mounting holes because it's a PGA module. So invariably the high power designs, correct? When you have a 662 contacts or 330 plus contacts, the CPU is going to be a powerful CPU, correct? Then it's going to throw a lot of heat. So you can consider a mounting option, or whether it's a fan or without fan, you can have a hole or how you want it to take care of in the carrier board initially itself, so that you don't get into the surprises in the later point. And also we have seen because it's tightly coupled. So our first module, if you look at there is no space at all. So you have the memory, both RAM and flash and Wi-Fi module and CPU and the power management area. So the hotspots were quite high, right? So it's better to plan initially itself with a proper simulation and bring your heatsink and heat spreader designs in the starting phase itself and provide the sufficient, the spread out areas or the you make sure that the entire SOM was properly thermally managed. So moving on to next step. So which one do you select in the sizes, correct? You have 4 different sizes starting from 0 to L, we said. So it is definitely based on your peripheral choices, correct? If you need multiple Ethernet all the way to 5 Ethernet, you can get it into the size L, which is quite high in the embedded industry we see. But for the networking application, it's very handy now. And you can have one display in all the specification except the zero size, that's a RGB. But one of the area we noticed is on the LVDS, correct? The LVDS is only available in the large size. So if you are going to big panels like LVDS panels, which is a much bigger size beyond 7-inch, now you get it only with the LVDS, correct? So it is a little bit tough to go with a smaller size because LVDS you don't get. Though RGB is available, but not many supplies were many displays were coming with the RGB nowadays. Now, another interesting area we saw is plenty of PCIe options, which is we get it now both into 1, into 4, and into 2 lanes, so across the module. Now, another area we have seen is really handy is GPIO. Correct. So if you look at Q7 or SMARC, you just get 8 or 12 GPIOs, which is always too tight for any carrier board designs. You need a lot of interclines or you need a lot of IOs for control. So we always ended up doing an IO expander in the carrier board. This is what we have seen in the past. But OSM being very small, but it is very generous in terms of giving the GPIO context because it has too many pins in the BG in the bottom. So you can have all the way to 40 in the size L, which is very, very handy for any applications to have for embedded applications. And in terms of size, you need to really look at the real estate available versus what are the things you are going to put, what kind of RF modules you are going to place. So it's kind of a little bit too tight in the initial design stage to incorporate which one to put, which one not to put. And if you go to size 0, it is very, very small. And we have seen with the area of processors we use from NXP, even some cases from Renesas and Qualcomm, but none of them we can fit it into the size 0. But any designs which comes MCU where most of the cases, no, the memories were built in, but you can go for a size 0 for a MCU based designs. This is what we have seen. And then how do you test these modules in the production? So this is one of the things we need to look at in the initial itself actually. For example, if you take a SMARC or Q7, you have the board-to-board connectors. So it's very simple. You can have a test jig with a breakout board. You can just program using your the programming, and then also test individual module before shipping. But in case here, because it has to be soldered into the bottom, it's going to be tough to replace the module every time because it's soldered. And also you need to go for a socket for this. And when it comes to the socket, it is an individual socket for every size. If you go to the 0 size, small size, medium size, large size, you cannot use a one single. At least today it is not available. And also the test jigs or the sockets were still not available. We have explored so much. But one of the good thing is, yeah, you can still customize. The socket vendors are ready to customize, but it comes with a customization cost, and also the sockets were not it's quite expensive also. And the sockets, after some time you put and close, because when you mass produce the modules, correct? So when you produce a 10,000 unit, 20,000 units, so one socket, even if it is a 20,000 times, you can close and open. But then for the next production, you have to buy another socket. So these are the challenges we see. So what we saw is, okay, most of the designs, correct, you can have a small header or a tapping point where you can bring a pins and come into contact and bring only the console on the module itself. It cost about some 6 or 7 the soldering joints in the top. So that's we have tried to do. So with that, we were actually very successful in terms of testing the complete module, though we cannot test all the pins in the bottom. But the module features, the CPU, RAM, power management, everything we were able to test through these small headers, the pin, just a test pin header. And also the specification offers an pins for the connecting the voltage pins. So you can do all the way to 8 pins can brought to the module, so that in the test jig carrier you can have an LEDs. So you can take whether CPU core power or the IO power or DDR power. So you can just connect, and it's very nice feature. It was, I think it's really thought about a feature from the specification committee. It's really good for the debugging and also during the production. So some of the challenges we wanted to bring it here. So one of the major thing is the RMA and field replacement. in terms of board-to-board connector based, whether you take it as SMARC or Q7, even for any other SOMs like a DIM type or whatever it is, you can just unplug. When there's a problem, you can unplug and repair it and plug it again. Even if you don't want to repair because you are in hurry to supply to the customers, you can just throw the module. You can always have a backup of the module. I can just insert it and go on the way. But in this case, since it is soldered, you need to have a special machineries because it's a PGA kind of module. Even for replacement, removing the module and again putting back the module. Okay, so you need special machineries. And not only that, so the complete system has to be. So earlier cases, the module vendor just get the module for the RMA. Now, whether customer will ship the module alone or the complete system. So most of the people do not want to ship the complete system back for the RMA. So it's put a lot of constraints in terms of RMA. And another one, as I discussed in the previous slide, the debugging is a little bit a tougher part here because it's very dense. You cannot have your own like a test points. Even most of the designs you will tend to go with the HDA design. So you will have a buried and blind bias. So you cannot even probe. Correct. So the debugging will be a little bit tight here. And also on the production, correct. So it is again, as I mentioned earlier, you need a socket or you need kind of special equipments. The ecosystem is right now not available. But what we believe is both the debugging perspective, the production testing perspective, the tools, the sockets, everything will evolve. And going forward in the coming year, you can see a lot of interesting options from the suppliers and also from the open market, you will get a lot of tools. So the point 2 and 3 will not be an issue going forward, but the point 1 definitely we need to take care both in terms of the product quality and also in terms of the field failures. So that is one of the areas has to be concentrated. And again, though we have these kind of challenges, but the size and the pin density, it gives a very nice, this specification is very nice for the one for futuristic, that's what we would say. For example, the SMARC, if you look at the area per pin, correct? Even with the smallest size, you get 4,100 millimeters square you need the size, and per pin, the area is about 13 millimeters square. Right? But if you go to the largest OSM, which is just a 3 mm square per pin, okay, so it is, if you look at, then it's 4 times, more than 4.5 times, it is tightly packed compared to the small even. If you look at Q7, at the same Q7 is one of the biggest area, but it gives the lowest pins, correct, 230 pins. And if you look at with the OSM large, which is almost 7 times more densely packed, per pin. Yeah, you'll have to take it correct at the end of the day. So everyone needs how many pins, that is different, but as a standard, it is defined. So you can put so much of stuff into OSM compared to the existing form factors. Even the DIM size, a lot of companies use, though it is not a standard. Today, there's a plenty of companies make a modules with a DIM size because it's a small size and more pin density. But the OSM outthrow every spec, and it is in the top. And on the cost, this is an interesting area where you can look at the cost, right? So we have seen some interesting result being we have same SOM available in the SMARC and also OSM. That's 8M plus we have. So when we did a comparison, correct, we have seen a really wonderful result in terms of the cost. Definitely the connector cost is not there now. And the PCB cost is very important because we did not realize this first, but then when we check the cost of the PCB, it's really less. Why? Because in the SMARC or Q7, you have to have a gold edge fingers. The gold cost, you are aware, is quite expensive, though it is the light density gold. But in SMARC, you need to have a 314 pin gold tabs in the top and also another 314 in the bottom. That means 630 gold tabs you have to use for SMARC. Similarly, 460 gold tabs you have to use for Q7. That reduces the cost tremendously in OSM case because it's just a unique type where we use. And there's another area we saw on the packaging and logistic cost, because in the SMARC or Q7, you need to have a big boxes to accommodate these modules. And then also the shipment cost, logistics, as the package is bigger and bigger, your cost is bigger and bigger. But here, the OSM can be just put onto the reel itself or into the normal trays where your kind of IC use. So we save a lot of cost in case of OSM. And some of the areas also adds up to the cost to the OSM. One of the things is assembly cost because you have the BGA bottom. but it's not so high because even the connector, the assembly cost is based on the per solder joint. Though the connector also you have to accommodate the cost. So it's a slight increase, which we saw. The main area we see is the cost where if your product quality is bad, and then you get into the lot of RMA cost because of the soldering module, you cannot simply replace, and field failures, it's very tough to replace. But at the end, when we saw that in terms of if you put it in the scale, but the OSM module cost is definitely much better. You can save a lot of dollars compared to the Smart Car Q7. So now I transfer to my colleague back, Taufik, so to run upon some of our latest development on the OSM and some final words before we take on to the QA. Thank you, everyone.
Thanks, Emmanuel. A very, very interesting deep dive on the OSM standard and how it has been, how the specs have been future-proofed. So building on this future-proof standard, we built the OSM on the i.MX 8M Plus, upcoming on the i.MX 8X Lite, also building the baseboard for the i.MX 8M Plus. I'm sure a few of you would also have the question, how do I evaluate the 8M Plus OSM from iWave? So where you can use this baseboard as a development kit for the OSM module. Now looking at the specifications of the 8M Plus OSM, the 8M Plus, as you know, is built for edge AI applications where it is integrated with a neural processing unit operating at up to 2.3 tera operations per second. So the OSM has scalability from the dual cord Lite and the i.MX 8M Plus cord. Also built with the provision for Bluetooth and Wi-Fi 6. This 8M Plus with the multiple connectivity options is built on the larger standard, the size L standard of 45 mm by 45 mm. And it is primarily built for edge AI applications, where the image signal processors and the dedicated neural network processor, which I mentioned, finds a fit in smart home, smart city, industrial IoT, and machine learning applications. Then in October 2021, maybe 3 months ago, NXP launched the i.MX 8X Lite SOC for automotive purposes, primarily for the telematics, V2X, and industrial IoT. So here the i.MX 8X Lite is built with 2 Cortex A35 cores plus the Cortex M4 core, with the main key value proposition being it has a security block with an inbuilt V2X accelerator and NXP edge lock security. So therefore, this NXP's i.MX 8X Lite SOC adds a more advanced security block with the complete accelerator elements. So V2X primarily is a key technology in the future, where it was originally envisioned for controlling traffic, but it is more and more getting into the vehicle-to-vehicle, vehicle-to-network application and different kinds of V2X applications. So what is the value proposition of iWave? So together with these system on modules, so how does iWave value add to the customers? So primarily the key 4 building blocks which we build on is through the timeline. So we enable customers both in terms of a rapid timeline as well as a delivery timeline through a strong sourcing and supply chain team. And over the last 2 years, we all know that has been a key trouble for embedded designers, system on module manufacturers, and companies across the globe. So timeline plus a strong supply chain team is definitely one of the key points which iWave tries to build on. The second is in terms of turnkey. So in case someone needs some software migration or in terms of hardware design development guidelines or taking care of the carrier board design, or for example, also take a single point of contact for SOM plus heatsink plus enclosure. So iWave is ready to take the complete turnkey responsibility for the embedded building blocks. And last is in terms of the business model. So building a flexible business model dependent on the engagement model of the customers, the roadmap. So we are very flexible and transparent on the building blocks of business model, timeline, turnkey, and a strong supply chain goal. And here are a few resources. For example, the OSM Standard explained, the press release, and in terms of data sheet. So I will also be sharing across this presentation to you where you can get access to these resources. And that brings me to the end of the presentation. So thank you. We will go ahead and take some time for questions now. And just a reminder to type your questions into the question box onto the right. So maybe Emmanuel,
So
sir.
yeah, we have a plenty of questions. I think I will try to answer them. So my colleagues, some of our my colleagues also here, they can also get into some deep questions. So first question I see from Alberto. So for similar specs of the processor, memories, etc., does the OSM standard suppose an increment of the cost compared to with smart standard? No, actually it is less because of the PCB cost and no connector cost. And yeah, the assembly cost is always subjectable with which EMS or contract manufacturer you do. But based on our experience, as Taufik shown, we have a OSM module on 8M plus. We also have with the SMARC, and we see the surprises in the price. Definitely, we see $3 or $4 less. And coming to the second question from the Pietro, is there a letter for the customers on the longevity for 10 to 15 years? Yes. Yeah, it actually depends from the vendor to vendor, but we provide, correct? So if we honor 10 years or 15 years, we provide the written letter to the customers. And the third questions from Kenji. So does OSM specify the level of ruggedness, vibration, etc. for the reliability? No, actually, it's no such a things. But actually, since it's a kind of BGA type, correct? So, so it can be depends upon everyone how they design the module. So the specification defines three different in terms of how your BGA ball can be, whether it's a ENIG or it's a BGA balls. So whichever be the level of ruggedness you want, you can choose one, but the specification does not define, okay, so this is the ruggedness you can bring in, or this is the ball type in the bottom you should use. Then I take the next question on Manish. So when is the start of the production of the 8M plus OSM? So we are already shipping the early sample for the with the evaluation kit. As you have seen in the previous slide, we have the OSM carrier board. It's a complete exploiting the OSM specification. So we are already shipping the samples. But the mass production order, as you know, the supply chains are too tight. So we are taking the supply chains with even from 24 weeks to 52 weeks. But the module production is starting from the second quarter, so which is very soon, in another 2 to 3 months. But already we are shipping this with the evaluation boards. And the question from the Jagan, does OSM support dual MIPI CSA connector directly on the module? Obviously not. So all the pins are coming in the bottom. You cannot have any connectors on the module itself. So it is up to you what kind of CSA2 connector you wanted to put in your carrier board. So you can choose your modules, camera module. Accordingly, you can put a connector. So the specification does not define any connectors. So all the pins, all the interfaces are coming in the bottom. And another one from Kenji again. So I see 4 different sizes. So exactly it is correct. So all the pins are overlapping each other. So all are pin compatible. So when you do a size 0, it is all the way pin compatible to SML. When you do a small size, it's all the way pin compatible, backward compatible, and the forward compatible to all the 4 sizes. So similarly, the voltage pins, the ground pins are defined such a way that it is completely pin compatible across all the 4. So one can have a common carrier board and can mount a 0 size or small size or M size or large size. For example, now iWave have a carrier board with a large size carrier board. We already have a 2 module. One is already in hand, which is a large size, and we are another one designing in small, which both will go to the same carrier board. So that is the main advantage of this specification. Another question from you is, I think, what is the pitch? I love to spec. I love to see the spec. Maybe Shami, if you have the answer, you can put the answer here into the chat window for what is the pitch of the ball in the bottom, so that I will move to the other questions to cover before we finish it off. So what is the operating temperature of the size cell? So operating temperature, it is defined by completely by the design. So the companies can fix based on the component use. As such, from the specification committee, there is no specific constraints. You can have industrial or you can have automotive. Even in the automotive, you can have much wider temperature. So there is no specific temperature, whether it's a size 0 or size M, size S, L. So it's what kind of component you use, what kind of reliability level you wanted to bring in. It's up to the designer choice, and the specification does not put any constraint over there. And another question from Anton. So how complex is designing the carrier board for an OSM when compared to the SMARC or Q7? Actually, it is much easier compared to the SMARC and Q7 because it is like you are routing an IC or you are routing an a kind of CPU, which is like a 330 plus pins or 660 plus pins. So you can easily break out. The main area you will have complexities in terms of the production, but in terms of designing the carrier board, it's much easier compared to the SMARC and Q7. So I will go to EMI and EMC effect. That's a very good question from the Ravi Shankar. Yeah, so definitely you need to take care a lot during your layout design. You have to plan your layers where the high speed comes, where the low speed comes, because the area availability is very less. It is too tightly coupled. The traces were too tightly coupled. You need to make proper spacing. So in the design itself, you need to take care, and then there is no problem in terms of EMI and EMC. And going on another question from Alberto. So in the ATM plus slide says 2 into LVDS. Yeah, you are correct and we are wrong. In terms of specification, it's a single LVDS, but it's a dual channel LVDS. You can, the specification defines one LVDS, but dual channel. You can have a 4 pair plus 1 clock pair in one group. So totally we have a 8 data pair and 2 clock pairs. That means obviously it's a 2 LVDS. You can have a full HD panels. But the specification says as a single LVDS, although you have a dual channel can be connected in the specification. And then the question from Venkatesh, can see Linux as OS and understand standard tools under Linux can work for regular application. Which development tool change for effectively using iOS, additionally EMI and EMC? Yeah, based here as the specification does not define any software stuff. It's purely comes from the silicon vendor. So which chip you use as a CPU? So you need to have use the same Linux distro, or you can have a different distro, whatever you want. But the specification does not put any constraint. And the EMI and EMC figures, as I already touched the answer from the previous one. The tool chain, again, the software tool chains, it's again depends upon the vendor, right? So if you use a NXP CPU, the tool chain has to be from the corresponding vendor, the chipset vendor. So the specification is nothing to do with that. And then another question from Alice. So do you have in roadmap also OSM with ATM Mini? Yeah, so right now we do not have, but our next is 8X Lite, but we might do this also. But we already see there are some vendors brought out ATM Mini. You can simply Google it because the ATM Mini was a little bit old processor by this time. There are many companies started doing OSM with ATM Mini. So we wanted to differentiate ourselves. So we are just always looking forward. So we are doing the 8X Lite, which is still not launched from NXP. But ATM Mini, we already saw 2 modules available in the market. So another one is sharing the presentation. Definitely you'll get the presentation, the link over the email. And next question is, when will be an OSM testing specification standard? So it's a good question. So we normally, when the specification launch from the committee, we see the design guides and some more standard comes after some time. Maybe this answer gain or after some time you can get an answer if he has immediate answer. So we will answer you here. But in general, what we saw whenever there is a specification launched, the additional guides, the supporting guides and documents start coming out after 1 year, 1.5 years, 2 years later when the ecosystem comes more and more. So is it planned to release the ATM plus OSM with automotive operating temperature? Right now, we do not have plan, but we have the plan with the 8X Lite. The 8X Lite was starting from all the components, from all the perspective, we are doing with a complete automotive grade. But 8M Plus, why we are not done? Because the 8M Plus itself, correct, it was made for a AI kind of application. So we have not chosen the entire component portfolio with automotive, but definitely with the minor component changes, it should be possible. If you have any specific requirement, you can discuss with us. And then, do you have information about EDP interface compatibility? Yeah, so you can look at the specification. It gives the complete information and pinout. In terms of the displays, definitely we have to get into details which display and what kind of things, and need to check the EDP displays for sure. And similarly, another question at Quad Max OSM, that's an interesting question. We have thought about this, but still no concrete plans, definitely. But I'm sure there are so many people who are developing with SJet. You can see an interesting things start coming in all the way down this year, whether it's a Quad Max or even you can see equivalent processor from the other chip vendor also. So will you offer 95 and 97 i.MX? That's a question from Joe Hill. Right now, yeah, 95 and 97 is too early to commit from NXPs because it's still not launched. Documentation also still not launched. But we know i.MX 93 is going to come first. So definitely i.MX 93 with the OSM you can see. But 95 and 97, maybe it's too early to discuss about this. And another question from Uvis, are you providing an application note to solder properly the SOM and what is critical? Definitely yes. So for all our modules, we have the detailed design guide, correct? So we can provide the design guides will provide all the stuffs, how you have to design a carrier board, how to put the OSM module, how to put the pins. And you can also make use of our free support for reviewing your schematic, especially on the OSM pinout area. And also we can also review your the layout, how did you put, so we can review your mechanicals and make sure nothing goes wrong. So those level kind of support we can always provide. I hope we were able to answer most of your question. I know a couple of questions, one from the design guide from the SJet and one more from the pitch. Definitely we will answer you specifically and we will get back to you.
So one more question, Emmanuel. Will you have i.MX 8 ULP OSM in the roadmap?
That's a good question. Yeah, it's nice to have because ULP is for a wearable, correct? And you have the zero size and ULP definitely, and we need to check how to fit in into the zero size because it's for a wearable. Correct? Wearable must be very, very small, and that is must be interesting. And yeah, ULP is getting launched. We need to consider this point. Definitely, we will put into the plan, and you can see our roadmaps sooner. So we will give a minute. If you have anybody has any more questions, you can just put, or if I have not covered any question, maybe you can also prompt me. I'm sure I have gone through most of the questions. And Samim had answered your UV's question. The pitch is 1.25 mm. So there's another question for smart carrier boards. There's a carrier board design guide available. Is it also available for an OSM carrier? Right now, no, but we expect soon it will be available from SJet. As I said, the supporting auxiliary document normally comes after a year. I'm sure some draft has been already made. You can expect this soon from the SJet. And what kind of sockets do you subject or use? Okay, so we had explored a lot of socket vendors, correct? And we have got some of the quotations in terms of customizing for, so first we are getting one for large. It's not so expensive when you get like one or two, like correct, $1,000 or $2,000, but it's quite expensive when you wanted to use that for the mass production. And almost everywhere you get from $600, $800, $1,000, $2,000, but it's not so good for the production perspective. Though you can use 20,000 times, they guarantee. But in terms of when we produce modules like 100,000 unit a year, it's definitely a little bit expensive than the current method we have for the Q7 and SMARC, but we strongly believe that this ecosystem will evolve, and sooner we get sockets at much cheaper cost. Maybe the 1 year down the line or 2 year down the line, the cost will go much slower because this gives a lot of options for the socket vendors, correct, for the ecosystem to develop and sell. So definitely, right now, standard sockets were not available for a OSM spec, at least from our search perspective. We all at least approached 4 or 5 socket vendors. Right now, no such things are available. But yeah, we hope soon it will, because we are now signing in with one contractor. So as soon as we buy, they may put it into as a generic product. So sooner you will get it. Similarly, the spacer PCB iWave also already have, as I mentioned, a large and small size, which will be easily available. So does the power button affect the PMIC on the SOM? No, it does not actually. So it's how we implement, correct? So you need to have a power button in the carrier board. It does not. So it depends upon the which PMIC and which processor you use. But in general, in the design, it's taken care. It does not affect.
Looks like we have covered all the questions almost towards the end of the webinar. So we'll just maybe give a... So Wolfgang is also asking about the deep sleep mode.
Yeah, again, this is a processor dependent, correct? So, and the software implementation. Maybe we can take this question separately, correct? As we almost finishing. Yeah, how are the prices compared to the standard smart module? I think we already touched on this point. Definitely we save $3 to $4 for the same spec. Even you cannot have Ethernet 5 in the OSM, in a SMARC you can have. Besides, even you just rule out the Ethernet 5, we see that for equal one-on-one, we see that OSM will be the less price. So do you have experience with the 2x2 edges of footprint and how to handle the PCB panel and PCB separation? Yeah, we can get on this point. So some of our EMS, we have been struggling with the similar points, correct? We can get back to you on this point, specifically on this one.
So looks like we have covered all questions. So I think thanks everyone for joining us today. And I would request you to take a screenshot of this slide. And in case of any questions, you can reach out to any of us, myself or Emmanuel. And in case of any questions regarding the SZ standards, you can always reach out to Ansgar from SZ. So it was a pleasure being with you today and looking forward to seeing you again soon. Thank you.
Thank you, everyone.